I would like to introduce Scott Shell, who is a strategist with the ClimateWorks Foundation and the Global Industry Hub, working to decarbonize heavy industry around the world, including cement, concrete, and steel. Scott is a fellow in the American Institute of Architects and spent most of his career as a partner at EHDD Architecture in San Francisco. He led the design of many university research buildings and independent schools, including a number of the first net zero energy buildings in collaboration with a talented team of architects and engineers. Peter Rumsey, the founder of the Stanford BDLA, was unable to make it today, but he wanted to emphasize the groundbreaking projects that he worked on with Scott before his current roles and how crucial his work has been to changing the building decarbonization industry. And take it away, Scott.
Wonderful. Thank you, Lindsay. Welcome, everyone, and thank you for joining us. So here's one of those projects that Peter and I worked on together. It was one of the first net zero energy buildings for the Packard Foundation. And the formula was very simple. It was a very energy efficient building that was then all electric with no fossil fuels. And that electricity was provided by clean, renewable energy. That approach is now scaling rapidly. And you can see in the next two graphs the impact that makes. A study that the Carbon Leadership Forum recently completed of 30 projects in California showed that if a building has gas for heating and electricity for other uses, the operational carbon is almost doubled the embodied carbon in the building materials. However, if you have an all-electric building in a state like California with a clean, low-carbon electric grid, it's reversed. The embodied carbon is now double the operational carbon. So realizing this about 4 years ago, I decided to shift from a focus on architecture in general and a lot of operational carbon, specifically to the building material world. And I moved over to ClimateWorks, to the heavy industry program. So heavy industry is responsible for fully 1/3 of all global greenhouse gas emissions. It's shockingly large. Compare that to transportation down below. All forms of transportation is much larger. It just hasn't gotten as much discussion because people thought maybe we don't know how to do it. But we actually do know how to do it, and it's time to get on with it. Heavy industry is concentrated in a few very large sectors. Cement, steel, and chemicals are the primary sectors that we work on. When I say we, I mean both the ClimateWorks Foundation and Global Industry Hub. These are philanthropies that support other organizations to decarbonize these industries. Just cement alone is about 8% of all global CO2 emissions, almost as much as all passenger vehicles in the world. This one sector. So to understand how to decarbonize it, we first have to understand how cement and concrete are made. So concrete is the material that you see and that we build things out of, the sidewalks and buildings and so forth. Concrete is like Rice Krispie treats. It's a combination of aggregates and cement. Cement is like marshmallow. It holds the aggregates, the Rice Krispies together. This is a typical mix design for concrete. It's about half of these coarse aggregate, maybe 3/4 inch aggregate, and then quite a bit of sand and about 10 to 15% cement. So cement isn't that large a portion of the concrete, but it is responsible for almost 90% of the carbon emissions. So this is an area where we're really going to concentrate our efforts. So to make cement, you dig up limestone, you crush it, you mill it, you put it in a calciner tower and heat it up to about 900 degrees centigrade. That creates a calcination process, a chemical process that emits CO2. You then put that in a rotary kiln at 1450 degrees C, and that makes clinker. You grind up that clinker, and that makes cement. So here is that process in photos. Cement plants are typically located next to a limestone quarry because they use millions of tons of it. This is the Cupertino quarry and cement plant, now closed near Stanford. They drill a bunch of holes, insert explosives, blast that. They then dig up those rocks, put it in a dump truck, take that over to a crusher, crush that up into smaller rocks. Those smaller rocks go into a grinding mill, in this case, a ball mill that's full of steel balls, and they grind up those rocks, those limestone rocks, into a fine powder like flour. That's called raw meal. That fine powder is then put in the calciner tower. This is the tall thing you're seeing here. It has a series of cyclones, and that fine powder is swirled around, and super hot air flows through that and heats up all of that limestone raw meal to create this calcination, this chemical conversion of that material. That material then goes into this brown round tube. That's the rotary kiln that you see going off to the left. It is sloping down and to the left, and that raw meal flows through it and turns into clinker as it's formed. This is the end of that kiln. These are big things. There's maybe 10 or 12 feet in diameter, so you could drive a car through it. And they have an enormous burner to get this material up to these very high temperatures, much hotter than lava. Most of the fuel for that is powdered coal or powdered pet coke, so very, very high carbon fuels. And then the clinker spills out of the bottom of the kiln there, which you see. So you see the clinker here in the left, it's kind of these rock-like nodules. You then have to grind that clinker again to a very fine powder to make cement. You can do that in a ball mill like we saw earlier, or you can do it in a vertical mill as shown here, which is much more energy efficient. And cement is made on a huge scale. A typical cement plant is 1 million tons a year or more. So that's 100 trucks like the one you see here every day. It is a big logistics business. And if you want to change it, you have to be able to work at that scale. So where does all the CO2 come from? So you see here the CO2 numbers associated with each step of that manufacturing process. And you might think it's all that mining and transportation, but no, it's actually this calcination process in the preheater and all the fossil fuel used. Limestone is calcium carbonate. When you calcine it, it splits into lime and CO2. Almost half of the weight of that limestone is released as carbon dioxide. So picture that big old dump truck full of rocks. Almost half of that weight is released as CO2 in that calciner tower. And then there's a lot of fossil fuel to get up to these very high temperatures. So that's also a very large contributor. This process emission, this chemical conversion is over half of it. The fossil fuels are the next bit. The key thing is not that it's that carbon intensive as a material, it's that we use so darn much of it. We produce more concrete than any other material globally. We produce about 30 billion tons of concrete per year. That's about 8,000 pounds for each one of us. Every person in the world consumes about 8,000 pounds of concrete per year, an astonishing number. If you compare that to lumber, we produce less than 1 billion tons of lumber a year. So we're convinced there's no other material that can replace concrete as a building material just because nothing else is available at this scale. So if we have to use it, how do we decarbonize it? So there's lots of roadmaps out there that describe pathways for decarbonizing cement. This is the roadmap from the Global Cement and Concrete Association, and they stack up a number of different strategies. The top one, the light green, is designing more efficient use of cement and concrete in our buildings. The next one is efficiency in concrete production. That's especially things like using mechanical mixers instead of mixing by hand. The next one, the light orange, is the one we're going to talk about mostly today. This is saving in cement and binders. This is using less clinker. The next one is basically energy efficiency and then carbon capture. The carbon capture one, the purple one, is large here, but in our view, it's by far the most expensive. And so we want to shrink that down as the last strategy we use and use all the other strategies that are more cost effective first. These are the cost of those various levers. You can see the zero vertical line kind of on the left center there. Those are cost neutral strategies. To the left are cost saving strategies. And obviously the purple strategy there, carbon capture, is at $80 to $110 a ton. And that is predicted to double or more than double the price of cement. On the other hand, we're very fortunate to have these two kind of orangey colors that are actually cost savings. The clinker factor, these savings in cement and binder, is the one that we think has the potential to scale up and make quite a big difference. What that means is ordinary Portland cement is mostly made with clinker, and you can replace some of that clinker with something called supplementary cementitious materials, SCMs. The SCMs that you hear mostly about are fly ash and slag. Both of these are dependent on coal power. Fly ash is the ash that is emitted from generating electricity from coal power plants. And slag is a byproduct of producing steel in a blast furnace. So these materials work well as SCMs, but they are from coal, and we are phasing out those coal industries. We're working hard to get rid of those. And so those materials are declining. And in fact, it's already getting hard to get some of these materials. You'll also notice that down below those LC3, limestone calcined clay cement, which is the topic today. Also natural pozzolans, these are like volcanic minerals where the volcano did the work of heating those materials up. In the black, you'll see these percentages. That's the percentage of clinker that's remaining. So ordinary Portland cement at the top, that's 95% clinker. That's the really high carbon part, right? That's the part that releases all those process emissions in that chemical conversion. These other materials are very, very low carbon because they're more byproducts. So the slag and LC3 are at 50% clinker here. So you're almost halving the amount of carbon emissions when you make cement and concrete with these high replacement levels. There's another challenge with these SCMs is that they're just not available in large enough quantities. You can see here the Portland cement, we make over 4 billion tons of Portland cement globally every year. And there's only about 8% or 10% or so as much fly ash or slag as there is cement. So it can never replace at a high level on a global basis uh, uh, the cement, the Portland cement or clinker in those blended cements. The bottom line, however, you'll see calcined clay. Clay is one of the most common minerals on the earth. It's broadly available around the world, so it's near where you need it. And so we think that that is the globally scalable solution. Now, we still support using these other ones while we have them, but we need to prepare for the future and for today where we can get to much, much higher clinker replacement levels with these supplementary cementitious materials. So let's take a closer look at LC3. So it's a mixture of ground limestone and calcined clay and cement. So on the left, you see OPC, or ordinary Portland cement. And on the right, you see LC3. This is LC350 with 50% clinker. So you replace about half of that clinker with 30% calcined clay and 15% ground limestone. Now, this is not limestone that goes through the kiln. This is just ground up. So it's very, very low carbon. In both of them, there's about 5% gypsum added to control the set time. LC350, there is still some fuel used to calcine the clay. So instead of getting a 50% reduction, you get about a 40% reduction in CO2 emissions. There are, however, continued progress on increasing the amount of calcined clay and lowering the clinker content. So LC335 with 35% clinker is now a code approved material in some jurisdictions. and is being produced in a few plants globally. So this is really driving down the carbon emissions of this blended cement. I'm going to show you three different ways to make this LC3. The first one is you make it in a rotary kiln, just like you make cement. Uh, in fact, this is a former clinker rotary kiln for the Ash Grove Cement Company, a subsidiary of CRH, in their Nebraska plant. They are actually retrofitting this kiln to calcined clay instead of to make clinker. Um, it's very low cost to retrofit it. You calcine clay at a much lower temperature at about 800 degrees than clinker. Clinker is about 1450 degrees. So your fuel costs go way down. The fuel cost is about a third the cost of the cement. So producing the calcined clay is much more affordable. And retrofitting existing kilns is one of the most cost-effective way to produce a plant. There are actually quite a few excess kilns around the world. There's a lot of excess cement production capacity in China, in Southeast Asia, and some other places. So there's kilns that could be retrofit to produce this. The other primary way to calcine clay is in a flash calciner. This is the tower that you see on the left. It's very, very similar to the pre-calciner tower that we saw in cement production. It's a tall tower with a bunch of cyclones in it. It circulates that powder, suspends it to transfer the heat to it to create that chemical activation, that chemical conversion. Although in this case, there's no CO2 in the clay, so you don't have those process emissions, just the energy emissions. So this is the flash calciner. Those are the two primary ways. There's a new technology that's just coming out that's called mechanical chemical activation. And this is the ThyssenKrupp Policius Mecha Clay. They've just gotten several awards from the EU Innovation Fund to develop this new type of technology. They're building some pilot plants using this process, which is lower carbon than the thermal conversion process in the prior two examples. And they're targeting below 40% clinker. So it's a continued progress to keep lowering the carbon content of these materials. We're now seeing some exciting big new projects built using the LC3 material. For those architects in the group, you know BIG Group, Bark Ingles Group. This is the Milan City Wave project that's under construction. So obviously a major high-rise project. In Lausanne, Switzerland, this is the city where EPFL University is located, and this is where the LC3 research team is based. This Tilia Tower has now topped out. I'll get to go see that here in another month or so. So obviously, major high-rise project. One of the great characteristics of LC3 is that it significantly improves the durability. This is actually true of many SCMs, is that they make a better concrete. So on the upper left there, you see a electron microscope image of cement. The needles are the calcium silicate hydrate. On the bottom, you see a drawing of cement hydrating. You add the water to it, and these needle-like crystals start growing until they all interact, and that's when the concrete sets and hardens. All these interlocking needle-like crystals. But you'll also see these hexagonal shapes. That's calcium hydroxide. So that's kind of unreacted material. The SCMs actually react with that calcium hydroxide and make more of the CSH. So they complete the reaction of the CSH and make more of it. This also makes the concrete less pervious, so that less water can get into it. One of the primary mechanisms for degrading concrete is water getting into it through perviousness or cracks, degrading the rebar. That rebar then rusts and it expands and it cracks the concrete. Another mechanism is ASR, alkali-silica reactivity, and that's what you're seeing in the upper right-hand corner. In fact, that Ash Grove plant that I showed earlier In Nebraska, they have a serious problem with ASR, and the Department of Transportation is very keen to solve that by using the LC3 cement. So they are supporting the use of these high clinker replacement cements like LC3. Obviously, if you're going to pave a highway with something, you have to be darn sure it's going to work. So there's a lot of testing and verification going on. On the bottom two images, this is the Min Road test track outside of Minneapolis. They have a circular loop that they're running a test truck on that you see in the foreground there. And then they also have an extra freeway lane, and they pave different types of new materials on that freeway lane. And then they divert traffic onto that lane for a year or two and monitor performance and do all sorts of tests to ensure that it's going to be durable and long lasting and strong and not crack and all these other stuff. In the upper right, you're seeing some of the testing from a similar facility, although not as large, at the University of California at Davis. They have a lab to slab program. So they have an extensive research lab there, but then they also build slabs and they actually run heavily loaded trucks over it and demonstrate it in the field. So they've been also doing a lot of field testing and verification for LC3 recently. So all of this testing and verification is to ensure a good performance for these materials that are new to the market. I'd like to talk a little bit about where cement is consumed, because this has a lot to do with the strategies we use to roll out these new materials. This is the chart that shows the geographies where cement has been produced and is projected to be produced out to 2100. You'll see just the enormous growth in cement production in the last 30 years, especially in China. China has just gone through an explosion of construction and urbanization with 1 billion people moving into the cities. That their cement use has peaked and is now declining, and other emerging economies are rapidly growing to fill that gap. On the bottom, you'll see this blue bar. That's the OECD. Those are all the developed countries. That's all of North America, all of Europe, Japan, South Korea, Australia, on and on and on. Those economies are only about 10% of cement consumption. They've built most of their housing and most of their buildings, most of their infrastructure, and are not growing as much. So it's in these other developing economies where 90% of the cement is going to be used. Shown another way, here's where projected floor area is for the next 40 years. Africa dominates. Very large population, early in their development cycle. So lots of people still moving into cities, building their housing, building their roads and infrastructure for the first time. China and India are next biggest. And so we really need to understand how to solve this problem in these economies. Now, this is the new Global Cement and Concrete Tracker, just released earlier this year from Global Energy Monitor. Each green dot shows a cement plant. There's roughly around 3,000 around the world. The diameter of the dot shows the production of those cement plants. A kind of typical plant is maybe 1 million tons, and the bigger dots are significantly bigger, up to 8 or 10 million tons for a plant. If you look at North America, you see those dots are kind of spread around relatively evenly. That's because cement is heavy and it's cheap, and so you don't ship it very far. So you tend to have regional plants that serve the population around where they live. The plants are also located near population centers because that's where the buildings are. I'd like to invite you to compare 3 geographies: China, India, and Africa. Each of these geographies has about 1.5 billion people. But look at the difference in the number of cement plants. China is almost solid green, and Africa is quite sparse. Africa is still newer in its development cycle. We want to develop a new type of cement plant, these LC3 plants, that are much more advanced, efficient, lower cost, more durable, and lower carbon. before we build out a new generation of these existing type of clinker plants. So that's a lot of what our grant making is focused on. So that was cement plants, maybe 3,000 of them. These are calcined clay plants. So maybe there's, maybe 20 or so of those around. Some of these aren't operational yet. Most of them are. They tend to be smaller because this is still kind of relatively new in its adoption phase. You'll notice that a lot of them are in Africa or Latin America. Well, why is that? One of the reasons is that in a lot of these geographies, they don't have good limestone reserves. We were recently in Ghana visiting there and looking at their plant, and they have essentially no limestone in Ghana. So they are having to import clinker using hard currency from places like Morocco or Turkey or Egypt. So it's very expensive for them for a basic material that you need to build your economy on. So they're very happy to use a local material, and clay is widely available around the world, especially in the global south. That plant we visited in Ghana is CBI Ghana. This is their clay quarry. They developed this quarry. They created a bunch of good new jobs there. The village that was located adjacent to it had very few jobs, so now they've got a great new source of income, quarrying it and driving the clay to the cement plant. And then at the plant, this is a much more advanced plant. Instead of just importing clinker and grinding it up, you have to understand the cement chemistry. You have to have a lab. You have to have lab directors like Peter on the left there and his lab technicians on the right. All of these are chemical engineering graduates from the local university in Accra. These are great jobs. These are bringing the high value work to their home country rather than just importing the clinker. So there are all types of projects that are built with LC3. This is Pallava City by Lota Group, the biggest developer in Mumbai. This is a city for 2 million people. This is a lot of concrete, all flat slab construction. They have been working with JK Cement to pilot LC3 cement, and JK Cement has recently started producing some. This is the upper end of the market. They have 3 ready-mix plants making concrete for this development. So they make concrete like we do. It's all in a plant. It's all computerized, all carefully measured. Concrete is pumped into the forms as usual. So typical international style construction. But most of the concrete in these emerging economies is not ready-mix concrete. Ready-mix concrete is typically served with bulk cement in trucks. Most of the market in these economies is in bags of cement that's mixed on site, either in the small mechanical mixer like you might see for laying brick, or by hand on the ground. In these methods, it's much harder to control the quality. On the left, you can see that a lot of the concrete is expected to go into single-family residential. A lot of this is self-built. It's people will buy a few bags of cement and they'll mix a little concrete on the weekend and they'll pour a little bit of a house. And then over time, they gradually build that up. So here is a look at those 2 methods. On the bottom left, you have hand mixing concrete. So they'll take 1 bucket of cement and 2 buckets of sand and 4 buckets of aggregate, something like that, and mix it up. On the right, you'll see this mechanical mixing. They'll dump in 2 wheelbarrows full of aggregate, and then a wheelbarrow full of sand, and then a bag of cement. So it's just, again, there's not the precision of measurement and accuracy of measurement. That tends to lead to more cement use. This also happens on bigger projects, much bigger than you would expect it. This is a 10 or 12-story high-rise that we drove past. And you'll see there's piles of cement, there's bags of cement, piles of sand, and piles of aggregate. These workers will carry that aggregate and sand over to a mixer by hand. they'll cut open a bag and pour it in there and mix it up in a portable mixer. Um, so since you can't control the concrete mix very precisely, what is in that bag is super important. And that's why we are big fans of LC3 because that is a very low carbon cement that can go in that bag and can still produce a very strong and durable concrete. One of the other main uses of cement is to make concrete blocks. A lot of walls, and in fact, in low-rise construction, a lot of times the concrete block will be the structure. These could consume a very large percentage of the cement in a country. Um, so here you see them on the left, making one block at a time. These are solid blocks, and most of the concrete blocks that we are all familiar with are hollow. Um, and there is some very exciting progress that's happening here. A former postdoc at EPFL in Switzerland, Dr. Alice Becerra, she's returning to her faculty position in Tanzania at the University of Dar es Salaam. And she's also starting a low carbon concrete block production. If you look in this chart, you'll see that the fired clay bricks are actually very, very high carbon. Then you'll see solid concrete blocks. These are next. By making them hollow, you reduce the amount of cement required. And then she starts adjusting the cement mix, including using LC3 50% and LC3 35%. So there's a dramatic reduction in the greenhouse gas emissions for these more efficient blocks. So that is my overview, and thank you for listening for that. And I see we have a number of questions. So we will now start the question and discussion section. Lindsay?
Yep. All right. From Kyle. Why is the term clinker used in place of Portland cement when you discuss the LC3 blend? It's my understanding that the clinker is the raw, bulky material that comes directly out of the kiln, and the cement is processed material that is used in the LC3 blend.
It's a good question. The clinker is the material that comes out. You grind that up, and then you make cement. Cement actually does have other ingredients in it, primarily that gypsum to control the set. And then a lot of people refer to blended cements as cement. So in India, for example, the SCMs are mixed with the Portland cement and ground clinker at the cement plant and put in the bags. So it's a detail, but that's how it works.
Okay. Your first slide about net zero building, can you talk more about how you cut down to real zero carbon?
So that was on the operational energy side. We didn't get to zero carbon on the material side. We're not able to do that yet. So that used a bunch of energy efficiency strategies, things like very efficient mechanical cooling systems and very efficient ventilation systems, extensive daylighting and controls to turn the lights off when there's enough light, really good insulation, all electric, as I mentioned. And then the roof is covered with solar panels that generates as much electricity as it uses over the course of a year. We did specify a lot of low carbon concrete on the project, and we used wood framing for interior partitions and things of that sort. That project was done about 15 years ago. Today, there is a new generation of materials that's starting to become available. The first cement plant with carbon capture and sequestration opened earlier this year in Brevik, Norway. It's a Heidelberg plant, and they're making about 400,000 tons a year of near zero emissions cement. It's expensive. It's several times as expensive as the cost of ordinary cement. And they don't actually, you don't ship cement very far. So there's a process called book and claim, where you use the local cement, but you get credit for their carbon capture there through an exchange of sort of like renewable energy credits. There's also the first demonstration plants for green steel are being built. Difficult to buy, but we are working hard to kind of make these near zero carbon industrial materials available.
Why can you not use the current kiln? The cement kiln can have temperatures up to 1400 Celsius. Why do you still need to retrofit the kiln?
It's not a major retrofit. It's things like adjusting the burner to get to a lower temperature, maybe changing the rotation speed, uh, changing the material handling that goes into it. So it's actually a minor and very low cost retrofit.
Question from Umer. The challenge in Pakistan for LC3 adoption is capital cost. CEMII doesn't need any CapEx and clinker factor is already down. There's not ETS or carbon credits. Financial advantage for sponsors isn't there or visible. How do how does one tackle it? No one cares about carbon reduction. They want to save money.
Yeah, no, I hear that loud and clear, and I think that's why we're supporting these lower cost solutions in those economies. When people are building their first home and there's a critical need for transportation, energy, water, and wastewater infrastructure, it's hard to ask people to pay a premium. So the cost effectiveness is absolutely critical in these economies. Um, we found that the LC3 will save about 20% in cost. That's primarily through the energy savings. And we have a project right now to bring some project financing on. The payback period for that investment is around 4 years. And so we're lining up some capital to help make those investments in these retrofits that will pay back over this short amount of time. Uh, we do have a partner at Ned University, Tariq Jamil in Pakistan, working on this. And he's a new partner, but we expect to see some progress. And he seems pretty optimistic that he'll be able to make some progress there in the years ahead.
Great. There are many cement startups such as Sublime Systems, Brimstone. Could you please comment on these companies?
Yeah, so I should have mentioned that. There's the LC3 gets you to low carbon cement and concrete, but not to zero carbon. To get to zero carbon, we're going to need another strategy. The one in the GCCA roadmap was the carbon capture, utilization, and sequestration. But the other one is novel cement materials. And the two mentioned, Sublime and Brimstone, are some of the most promising and advanced. So we're supporters of we are applauding their efforts and rooting for them to be successful. On the other hand, the cost are always a question. We don't yet know what those things will cost. And the requirement to build a new type of cement production plant at the scale of millions of tons and thousands of plants around the world is just a huge undertaking. So we are, like I say, rooting for them. We have helped support legislation. The Inflation Reduction Act included significant funds for those two companies. Unfortunately, those grants have been canceled to get those first demonstration plants built to sort of do proof at an industrial scale. So we hope that they'll find a way to keep those projects going forward, and we look forward to the results.
Great. Can you explain more why the LC3 cement is better than bagged cement?
So the LC3 can be used either in a ready-mix operation in bulk form or in a bag form. So it absolutely, in fact, most of it that's being produced is being produced in bag form right now because most of those plants are in Africa and South America.
Um, how much is steel slag recovery from global steel production, especially in India and China? I wonder if a study is being done to country level steel slag to cement production capacity to identify the gap more granularly.
A good question. We actually have a study underway to identify future projected slag and fly ash quantities in India in particular. Those industries are still growing in India. And so while we have them, we want to use them. It is clear, however, that there's not enough to get to this 50, 60, 70% replacement level. Um, and there just won't be. We support using it while we have it, but we also need to expand the solution set. There are also a lot of the startups that the previous question was mentioned. There are a lot of startups that are working on other supplementary cementitious materials. And so uh, we think that the one that will really scale is LC3, but there are others that work, and we have to see if they can get to this scale and lower cost.
Why is the US slow to adopt LC3 versus Europe?
So, it's a somewhat new technology. The research group at EPFL, Dr. Karen Scrivener, Shashank Bishnoi at IIT Delhi, Fernando Martinelli at CIDEM in Cuba, kind of developed this, but it's really kind of come on in the last 10 years. And you have to do a lot of work to switch construction materials. All of our codes are based on materials that have been around a long time and have proven themselves. You don't want to build something and then find out later that there's a problem. So there's been a sort of a long testing and demonstration project that has gone very well. But then you have to build the plants, and building plants takes time. You have to get investors. Uh, uh, you've got to design the plants, you got to build the plants, you got to open the quarries, you got to get the codes updated. So it seems slow, but on the other hand, things seem to be moving along pretty rapidly at the early stages. We're hoping to hit that S curve inflection point to where the adoption will kind of accelerate much more quickly now. And that's what we're working every day to do.
LC3 cement workability is challenging. Super plasticizers are important. Do we need more super plasticizers? Will this add to the cost of concrete?
Yeah, it's a great question. Obviously, we have some experts on the call. Um, one of the sayings that you hear is that geology varies with geography. And, you're digging up these minerals and making cements and making clays, and they vary a little bit from place to place. Then you make the LC3 and you can grind the materials finer or coarser. You can grind it with the cement or separately from the cement. And it's critically important to do really good recipe development for the LC3. And that's what many of our partners are actually doing every day. Um, the super plasticizers are an important part of that. Although in a lot of emerging markets, in the bag market, these admixtures can be challenging because they're mixing on site. So we would love to see further development in that, especially admixtures that could go into the bag cement. Um, but a great question, critically important to optimize these mixes for finishing and workability. Um,
Is the LC3 product from Ash Grove, Nebraska plant available for construction, at least the regional contractor?
So I've been trying to schedule a call with them just this week, and I haven't managed to get that done. My understanding is that plant should be done by the end of the year, and material should be available then. You know, commonly this is not shipped too far, so it'd be more a regional solution. But I would encourage anyone to reach out to Ash Grove and tell them you're interested and see if they can provide it.
Is there a business case to reuse demolished concrete as ingredient for cement?
Yes, there are several ways to do that. Traditionally, in many markets, demolished concrete has been crushed and used as base rock below roads or slabs on grade or things like that. So that's kind of downcycling. You can crush up concrete and use it as aggregate, but the shapes of those aggregates sometimes are not optimal, and it can cause more cement use, which could negatively impact your greenhouse gas emissions associated with your concrete. There's a new effort about trying to crush the concrete where you separate the constituents, the original gravel or aggregate, sand, and cementitious material. And that seems to hold promise. It is challenging because you do have to get all of that heavy material back to some central plant. And, it's expensive to pay somebody to go pick it all up and truck it over and reuse it. Um, it also takes energy to crush it and separate it. There's some, I believe, thermal energy involved in trying to recover the fines. Uh, so there's definitely a good bit of work and research done on that. Um, a number of the cement companies are investing in Europe, especially are investing in demolition supply chains and trying to get that circular economy thing going. Definitely further advanced in Europe than in North America.
How can architects better promote LC3 over OPC when working with clients?
So there are some clients who are able to move the market. The big clients, the tech companies, the big developers, the big real estate organizations. They have projects that are big enough and high profile enough, and they have budgets that will allow them to bring a new material to market. But for most projects, it's challenging to bring a new material to market. So for most of those architects out there, I think you focus on whatever SCM is available in your market and trying to optimize that to a 50% replacement level or better if you can. In my architecture practice, we used a lot of slag, and you could get to very high replacement levels, up to 70%. It's not really a scalable solution because almost all the slag in the world is used. So to some extent, you're diverting it from another location. The top recommendation would be to have a conversation with your owner, with your ready-mix concrete supplier, with your contractor, and with your structural engineer, and let them know that this is a priority and that you want these new low-carbon cement and concretes, and ask them to help you as a team effort get there.
Okay. Do we have the ASTM standards for LC3 now?
So good question. In some countries, yes. In the US, my understanding is there is a new ASTM standard out that should allow this. I believe it's been voted on in committee and approved, and it needs to go to the full ballot now, if I'm remembering correctly. But it sounds like that is about to get approved after some really good work from folks like Larry Sutter and so forth that have been sitting on that ASTM committee.
Are there any regulatory hurdles that prevent the adoption of LC3 in the USA?
Um, yeah, I mean, I think there are, it's complicated. There's, the codes and standards and specifications vary by jurisdiction. And so, for example, a number of engineers or architects or agencies like Department of Transportation's have prescriptive specs that mandate certain concrete mixes. Um, so one of our areas of focus have been with the DOTs because they have a bunch of top flight engineers on staff. They're spending taxpayer money, so they want to make sure that the materials are extremely durable and reliable. And so if they accept it, many other jurisdictions will accept it. So we're trying to use that as a kind of leverage point to change the market more broadly. We would encourage people to go for performance-based specifications instead of prescriptive specifications, and to remove a bunch of exclusions that are not necessary. The National NRMCA, National Ready Mix Concrete Association, has a good list of top 10 things that they recommend. So if you Google NRMCA top 10 strategies for low carbon cement, you'll find that. The RMI has a good guide on performance-based specifications. And the GCCA, Global Cement and Concrete Association, has a good series of recommendations for what level of carbon emissions you can strive for. That's kind of based on letter grades like A, B, C, D, E, F. So those are three good resources to check out.
What do you think it will take for those companies to scale besides money? Is it education, early adoption, risk takers, etc.?
Um, it's a lot of those things. So for a long time, it wasn't really available for people to try out. And now there's, this maybe 20 or so plants around the world, so people can get their hands on the material and hands on the material to try it at scale. It's one thing to make a little bucket full of it and play around with it in the lab, but a lot of concrete is about how it works in the field for the contractor, for the finishers. So going back to that excellent question about, placing and finishing it and admixtures, you want to make sure that it works for the people in the field that are doing that work, and they need to get their hands on it to try it. So we're trying to get these plants built in a variety of locations around the world, so that more people can try it. And we think that since it's going to be cheaper, once that happens, the adoption will accelerate. But there's a lot of education, required to get people to try something new. So many of our grantees are out there doing that work, meeting with companies, uh, talking about the advantages, talking about the cost savings, talking about the improved durability, and helping them to try and implement these new production methods.
Are there any LC3 production um, in the Bay Area?
Um, There have been some experiments. There is a company called Pure Base that's located a little south of Sacramento. They have traditionally, it's a mining company, and they've produced a lot of silica for making glass wine bottles. Um, they have a lot of tailings, a lot of leftover material that has very good high kaolinite clay in it. So they are perfectly positioned to produce this. They've been doing work on that. They've proven they can do it, and we're kind of waiting for them to get a plant set up and built.
What's the cost of LC3 in comparison to OPC? What's the cap investment for a LC3 kiln?
So we think, the longer term, we think the price will be about 20% lower than OPC. It depends on a number of factors, including, how much you spend on your plant and how far away the clay is and so forth. Um, but we think it should be about 20% cheaper. The cost of the plant varies a lot depending on if you retrofit an existing kiln, that can be very, very cheap. There are some rotary kilns that are very low cost. There's a company in Portugal called IPAC, IPIAC. They make very, very low cost kilns that are produced and assembled in shipping containers, and they're shipped out and they're designed to sit on the ground, so you don't have to do a bunch of foundation work. It's very low cost. On the other hand, if you want to do a flash calciner with a big tower like that, that can be quite expensive. So, the EPAC rotary kilns or other rotary kilns can be, sub $10 million. The flash calciners can be multiple times that. But they should pay back, and we're working to get financing available to enable those things to get built.
Have you talked about clay variations? How do you tackle the variations?
Yeah, no, it's a really good question. So the LC3 project team, that's one of their main jobs, is they talk with cement companies, educate them on it, and if they get interest, then one of the first things they do is go and try and find the clays near their plant. So they have a geologist that goes out and helps them, and then they'll take that clay back to their lab and test it and do all the material analysis and help develop the specific recipe for that clay and the other minerals that they have. Um, there's some new efforts underway to help find that clay. One of them is looking at remote sensing, perhaps via drone or airplane to identify clays. Um, there is this new technology that I showed that mechanically activated clay from ThyssenKrupp Policius. They say they can use a wider range of clays. So uh, all of that sort of research has to be done, and that's where you bring in the technical experts. In North America, there is a new technical resource center focusing on LC3, and that's at WJE in Chicago. So it used to be Wis Janie Elser, now it's WJE. They have one of the top cement and concrete labs in the country, and they are the experts on LC3 in North America.
How much time would it take to have the Department of Transportation include LC3 in specs?
That's a good question. Uh, you know, um, as part of the Inflation Reduction Act, there was a lot of money dedicated to FHWA to work on low carbon construction materials. To help that process, we set up the RC3, Reduce Carbon Concrete Consortium, and that was done in conjunction with the American Concrete Paving Association. So if you Google ACPA, American Concrete Paving Association, and RC3, you'll find their website. Um, a lot of that money was canceled in the new administration, but some of the states had already received their money, and some other states want to continue working on it. So they are working on this consortium right now to develop these mixes, test and validate them, and update their specifications and standards to allow them. So that's probably the best point for that.
Oh, just one more here. People also criticize the color of the LC3 cement. Can you comment?
Yeah, so uh, there are some examples where it kind of comes out with a reddish or pinkish color. And the folks at EPAC, this clay kiln developer that I mentioned, said, well, that's because it's cement people operating it, not clay people operating it. Those of us in the world of clay know how to deal with that. There's color correction, and we've seen very good examples of it. So it's a known, understood technical process to correct it, and you get color very similar to normal cement. But you have to know what you're doing, and you have to focus on that. And but that I think there are good solutions for that because it's funny, a lot of people don't seem to love the appearance of concrete, but then when you change it to another color, they don't like that either.
Right. Well, I want to thank you, Scott, and also remind everyone that there's another webinar on December 11th, the same time, The Unreasonable Goal, How Infosys Proved Radical Efficiency is Radically Profitable with Rohan Parikh. And I want to thank you again, Scott.